So next, I'd like you to get your isotopic penny bag that we set up yesterday. All right, your bag of isotopic pennies. And yesterday we got those all set up. And we're going to head towards the Cliff Notes version today too. So what I would like you to do is set out for me, if you could, the ocean standard. All right, ocean standard is going to come out. And we're going to put out cores 1 through 6. 1, 2, 3, 4, 5, 6. All right, so 6 cores are coming out. And the ocean standard. So that is the setup you need. Clear out some of my other stuff here. Salt water. So we need 6 cores and we need your electronic balance out is what we're going to need. And Lauren, you want to start a new recording? Or you guys are on it?
I did already. I just wanted to splice that last little bit onto the other video. So we're good.
So we don't have, Bill, we don't have a way to tear our container. Like we tear the container before. We don't have a way to do that here.
No worries. As long as you have your scale, we're just going to not even use a container on this one. We're just going to put things right on the balance. Remember, Rose, I came from teaching like high school kids. These have got to be very forgiving labs, you know? Things you can't make.
Right. Sorry, I just wondered, you know, I understand.
Yep. No,
sometimes they ask, you know.
Very forgiving. Yep.
We don't have your screen, Bill. I don't know if you're going to share that.
Just yep, I'm just getting around here. Let me start the next one.
Thanks.
And am I sharing to you guys now?
I know, we see you.
No. All right. All right, now I should be sharing to you now. Is that correct?
You're good to go.
Oh.
Okay.
So,
you guys are my heroes teaching in this mode all spring. Here's my.
Do we have to put the cookies in these classes?
I'm sorry, Rady, I didn't quite hear you.
No, do we have put in ocean standard to understand, you know, isotopes, that cookies, the points in these classes?
All we need out, Ready, is you need the ocean standard one. So yesterday we set these all up yesterday. So the ocean standard should have 5 pennies in it, and then
right.
Yeah.
And then just set out cores 1, 2, 3, 4, 5, and 6.
Okay, I got it.
So we're just going to do the first half. I think we're going to get a nice relationship, and then from that we can extrapolate what the rest of it will look like. All right. So that's what you need out for today. Instead of using all 12, we're just going to do the first 6. This is one of the main proxies that climate scientists use to go back and recreate the Earth's climate past. So we're going to take a little bit of time and build some background knowledge here, if that's okay. In this case, if you look at the ice core, they chop out that top little place, and that's where they measure isotopes from. I believe, I don't know this for sure, but I think there's 2 sets of isotope things there. I think they look at hydrogen isotopes and they look at oxygen isotopes. Those are the 2 proxy measurements that they can make for temperatures.
There is a problem, Bill. The scale is not sensitive enough It doesn't measure anything. It only gives 0.
Yep, well, we haven't measured anything yet, so just leave that scale. And Rose, the only thing I would tell you is make sure that the units are on grams, and as long as it says 0 grams, we're gonna be golden.
It says 0. Yep.
0, and it's grams, not ounces.
Yep. Grams.
You're golden. You're golden. So last time Louise sent you a $15 conductivity meter to substitute for her $70,000 gas chromatograph. This lab, she wasn't quite as generous. In this case, she just gave you a couple pennies. All right, but that's okay. With a couple pennies, we can substitute for our gas chromatograph and get our kids involved in activities that are going to expose them to some really high level content. So we are going to just do Cliff Notes number 1 through 6. We set these all up yesterday. Russ, you weren't with us, but I think you got it set up also. So I think we're all good to go. Let me get through this. So in your notebooks, the title of this is going to be Measurements Using Isotopes. And while people are writing this down, Russ, I'm going to go back to you. We set our notebooks up yesterday, Russ, and I don't know if you caught this or not, but we're using the left-hand page always for just your inspiration, your ideas for how you can take these ideas and change them and make them better for your situation and your school and your kids. And the right-hand side of the page, we're always using just for the actual notes from the presentation. So we believe that the left-hand page is probably the more important page here because that's actually what you guys are going to do back in your own classrooms and with your own kids. So again, we always want to start with some kind of a question that's investigable by the kids. So in this case, we're going to go, how does the temperature? And in this case, temperature is going to be a proxy temperature measurement. So we don't have a way to actually measure the temperature sitting in our classrooms 400,000 years back. But we do have a stand-in piece of data that can stand in and be a proxy for the temperature. So in this case, we got the dependent variable for this investigation is going to be what's the temperature going back in time. Our independent variable, again, is going to be just that thousands of years back into the Earth's history that they get drilling further and further down into the ice. All right, so if our question is how does the temperature of the planet change if you look back in the Earth's past, we have to have a way to get to the temperature. So temperature is actually related to something called isotopic deviation. So isotopic deviation, if you start to break that word down, we're going to be looking at isotopes today. And we're going to look at deviation. So this is almost like Leanne asked me in the last breakout about that tree index. What was the tree indexing? It was like a constant value that they were always referring back to. Here again, we're going to look at a deviation. So we're going to have a constant value. And we're going to see how our measurements vary or deviate from that constant value. And that's what the scientists do when they look at this thing called isotopic deviation. So here's the background on this. And again, most of you, I'm preaching to the choir. Let me just make sure that everybody at least has a little fundamental background. If you're, earth scientist, maybe this was a long time ago on chemistry, but oxygen has numerous isotopes out there. 90% plus of, or 90% of oxygen out there is oxygen 16, just 8 protons, 8 neutrons. So if you have a water molecule with regular old isotope of oxygen 16, it's going to have a mass of 18. I'm sorry, with oxygen 16, the whole molecule will have a mass of 18. If you have heavy oxygen, though, there's also oxygen atoms out there with 2 extra neutrons, which would give you water 20 with oxygen 18 in it. So we're just going to refer to these as the oxygen isotope because that's how the scientists do it. They refer to it as water with an oxygen 18 isotope in it. This is our model. Every model has strengths and weaknesses, but this is really important that you and your kids would understand this. In this lab, 1 penny is going to represent 1 water molecule. And that's the model that we're going to be using for this experiment. So when I dump this out, that would give me 5 water molecules. Any questions on what these pennies represent? Because without that, it's just magic.
So 1 penny represents 1 water molecules.
That's right. Exactly right. And that water molecule, so if I really had like microscopic eyes and I was going to look at this water molecule, that penny is actually made of 1 hydrogen atom and 2 oxygen atoms. But that penny represents a water molecule. All right. All right. Now here's a fact that you need to know. These are the facts that this proxy is built on. The freezing point of O18 heavy water, it's a bigger molecule. Bigger molecules condense and freeze and boil differently than lighter molecules. So it leads to something called differential condensation. So if you just cool off a body of air, when it gets below the freezing point of water, that water is going to turn into snow or ice. There's a very slight difference between the temperature that oxygen with 18 turns into snow compared to when oxygen with 16, water with oxygen 16 turns into snow. It's not a huge temperature variation, but it is there. So when water is getting close to changing from the liquid state to the solid state, the first water to go is the oxygen 18. Here's another fact you need to know.
So the first goes is the O18, you said.
That's right. As the air cools off, the first water to turn into solid snow would be O18. So therefore, if it's snowing and it's fairly warm out, you would expect that snow to have a little bit more oxygen 18 in it compared to the oxygen 16, because the first snow to form is the oxygen 18. Now, again, we're on a teacher-to-teacher slide here. This is for your background knowledge. If I was going to do this activity with my kids, we would do none of this. We would just collect some data first and see what the story of the data told us. But for you guys are here because this is what you want to put in your head. You want to learn more about this ice science, and this is the nuts and bolts of the ice science, how these proxies work. So with that said, when the temperature is cold, there's more oxygen 16 condenses. So now we're talking all the oxygen 18 is condensed when it's cold, and then you get oxygen 16. So now we're talking about a relative difference. If it's snowing when it's really warm, there's both oxygen 16 in there, but there's all the oxygen 18 and just a little bit of oxygen 16. If it's snowing when it's really cold, you got all that same oxygen 18 in there, but now you got a whole lot more oxygen 16. So we're talking about relative differences in how much oxygen 16 and how much oxygen 18 are in the water. Oh, and here's one more fact you need to know. Ocean water always has more heavy water than snow, always. And by heavy water, I mean that's ocean water has more water molecules that contain oxygen 18 in it than any snow that falls. So those are the facts that you have to know to understand this activity from the teacher perspective. You don't necessarily have to understand that to just collect some data and make a graph. But for you as a teacher, those are the facts that you need to have in your head. Can you guys put a thumbs up on the screen when you're ready to go on past this? Yeah, give me the there you go. Thumbs up when you got the notes down. There you go. don't want to leave anybody behind here because these are pretty important facts. And again, these are all going to be up on the web, so we can go back and again, this might be the kind of thing you want to look at a couple of times for it to make sense in your head. All right. So there's our question. How much does the average isotopic mass of the sample deviate from an ocean standard then? That's the question that we want to ask ourselves here. So what we have to do first is we have to get an ocean standard. So what I'd like you to do is this, is could you take your ocean standard cup, could you dump those 5 pennies onto the scale and tell me what's the total mass of all 5 ocean pennies? So just go ahead and take them. And here we go. Just dump those 5 pennies onto your scale and let's get the mass of those 5 pennies. And then
0.55.
there you go. Get a calculator, and could you calculate for me the average mass of each penny in that ocean standard for me?
Okay, there are 4 of them. It will be,
There should be 5, I hope.
so it is like 1.1. Oh, 0.11, sorry.
Rose, do you have 5 pennies in your ocean standard?
I got 4. Oh no, I got 5. Sorry, one was hiding. So
Okay.
yeah, I got 0.50. Oh God, what happened to this? The scale is changing.
Yeah, I think, Rose, I think you've got some scale issues, which might be coming from having a scale that's not a $300 O-House scale. Instead, it's a $15 cooking scale. But maybe just turn it off and back on.
I did. Yeah, I'm going to look at it again.
Okay.
I've found these scales, if the batteries are low, sometimes changing the batteries helps.
Mm. So I got 15.5. That's what everybody's gonna have slightly different numbers. And
I have 19.4.
19.4, who said that?
Paramita.
Parmita, 19.4, holy smokes. All right, check that again. Did you subtract away the cup? Parmita, take them out of the cup and just put the pennies on, not the cup?
They want us to always calculate the average.
Yeah, so we're always going to get the average mass of the water sample that's in that cup. And again, each cup represents, the model here is each cup is a melted water from an ice core, and we're analyzing that melted water from an ice core. That's the model that we're using here. All right, now.
I got 4 grams.
So it sounds like we got some scale problems going on if we got 4
I know what is the problem. We have to remove the cap.
4 grams.
We gotta remove the cap, people.
There you go. Yes. So if this is the first time you're using your balance, definitely get the top off. That's great. I was like, 4 grams. What's happening here? We should be in the ballpark.
15. I know, right?
Give me one of those reactions, like where you put the thumb up so I can see them on your screen. Thumbs up if you're in the ballpark of 15. Are we in the same ballpark here? All right, good. Okay,
Yeah.
so good. Okay, so we should be in the ballpark of 15. So this is your ocean standard. Now, you need a formula to calculate mass deviation. So there is the formula for mass deviation. Isotopic mass deviation, you just calculate it by taking the average mass of the water in the ice core sample, and you just subtract it from the average mass of the ocean standard. Now, your kids don't have to know all that other background knowledge on oxygen 18, but they do have to know this formula, but it's just a simple subtraction formula, because now I could just say this: the isotopic mass deviation is going to be average mass of one of those ocean cores minus our standard, which is 3.1. So let's go to ice core number 2, shall we? Let's do the first one together. Ice core number 2 is, in this case, it's 170 years old or so. Can you dump those 5 pennies onto the balance for ice core number 2? And put our ocean standard away.
Bill, I have one question for the 5 ocean pennies. Should I take the old pennies or the new? Is there a difference?
Well, the ocean standard we should have set up last night. We did that last night where we set them all up and we put the right number of old and new and all the different ones. So if we, yeah, we should
No,
have.
I did it for, I did it for all the cups, you know,
Yeah.
all 11 of them,
Yep.
according to what you gave. But for the ocean standard, I'm going to show you this one, this cup.
Yep. Yep.
So I have 5 pennies.
Yep. You dump those on there, you get the mass of them, and you get the average mass of the ocean standard. And when we're done with that, we're going to put away the ocean standard. We're done with that for the rest of the day. And
And
let's,
then the one would be smaller than the mass is 14.95 because we have the new one in there.
well,
We had
remember-
5 old ones in the
remember
first
that in our model here, the ocean always has more oxygen 18 than the ice and snow. So you would expect that all the ice cores are going to have less oxygen 18. They're all going to weigh less than the ocean standard. So I got for my ice core number 2, I got about 2.85, something like that. So now you just subtract 2.85 minus 3.10. So I would calculate then my isotopic mass deviation for core number 2, ice core number 2 would be minus 0.25 grams.
So what did you get the 2.85?
So that is right here. That's the average mass. I just put all 5. These are the 5 pennies from ice core number 2.
Well, I got 14.86.
Okay, whatever you got is your data. Yep. So you get your own data. I got my data. But whatever your data is, then you take that mass, divide it by 5, and you're good to go.
So these pennies, the one that is, present time, are these the one that made from the cheap metal versus the copper?
Yeah, well, if you want to talk about real pennies, when we're done here, we can talk about real pennies, but we're going to talk about isotopic chemistry right now. So here you go. In your notebooks, let's get your notebook set up, and then I'm going to go ahead and give you guys some time to make some measurements. Your data table should look something like that. There we have an investible question again. And I'm going to give you 5 minutes or so to collect your data from those first 5 cores, and you can calculate your isotopic mass deviation from each one. And depending upon how quick you are, we can make another graph that looks almost like our carbon dioxide graph with the direct measurement, but now we're making a proxy measurement for temperature. Because remember, as you work back there, the warmer the temperature is, the more oxygen 18 we would expect to see. And the more oxygen 18 is in there, the closer it's going to be to the ocean standard.
Okay.
You can go open mic if you want. Feel free to ask any questions. We're going to work on this till 11:30 when Eric shows up. See if you can get your first 6 data points measured, calculated, and see how many you can get graphed. And
Bill, was there a reason why we skipped 1?
No, not at all.
Okay.
I probably need to take a new picture of cup number 1 and put it up there so we can do number 1 instead. I think in the previous lab, I stole that picture from my previous keynote and we used cup number 2 intentionally on the last one, but this one, no, not at all. And again, we did a lot of background knowledge. We did a lot of background with you all about the nuts and bolts of this isotopic deviation concept. But with students, all students really have to know, the only facts that they have to know is, hey, when the climate is warm, we expect to see more oxygen 18, and that sample is going to be closer to the ocean standard. When the climate is cold, we're going to see less oxygen 18, and the sample is going to be further away from the climate standard. If they understand that relationship, that's about it.
Okay. So, Bill, by using ocean standard, we found our 3.10. We find our 3.10 like a standard value.
He'll be right back, Rose.
Huh?
He just stepped out of the room for a second. He'll be right back.
Okay.
But Rose,
Thank
you should use your own standard.
So
You
if I
should
use
your
my own,
measurement.
okay, so I divide my reading by 5. Okay.
And then that's your, so for your standard, your cup, that you have your standard divided by 5.
Very close. 3.11. Okay.
Bill, just so you know, Eric is here, so you'll be introducing him.
Oh, tell them to pop onto the screen, join our lab.
He's on.
He's on. I gotta make my screen bigger then. It's gonna say no hiding in the waiting room. Yeah, oh, I thought you were out in your favorite tree farm there, Eric. So if you have a graph made, hold it up to the screen so Eric can see what you're graphing. And and Eric, they've already got 2 or 3 questions for you waiting in the waiting.
Sounds good, Bill. Love to start with questions before we even begin.
So we have a 60-second warning for Eric. We're going to stay on schedule here. And then we will come back and put the final touches on this. Actually, I've seen some of your graphs. I think some of your graphs are starting to look like this again.
Oh, my problem is I did all of them.
Rose, you're an overachiever.
I was curious, you know.
Rose, you're the kind that never wants to read the Cliff Notes. The Cliff Notes, you're a good student. That's why you're an instructor.
But I never finish anything on time. That's my problem.
Oh, that's not a problem. That's a mark of somebody who does a good job.